Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 5 a.m. on Saturday in London. We're broadcasting live from Thousand Oaks, California.
Before we get started, I've been finding some cybersecurity info and was wondering, it just inspired me for, I thought, would you like another episode of cybersecurity? It would be a little bit more crunchy and go into some of the details a little bit more than the last one. So just let us know in the comments if that would interest you. If not, we'll do something else. But if it will, then I'll start putting it together for you. Thanks.
Excellent. Thank you, Jeff. So tonight we have a citizen science project known as Burst Chaser. We'll be back in 8.3 seconds. According to Zooniverse, in this project, they need your help on classifying light curves of gamma ray bursts, GRBs for short. One of the most energetic explosions in the universe. Gamma ray bursts can relate to supernova, black holes, and neutron stars, but their true nature is hidden behind the diverse pulse shapes. We need your help to classify these pulses for more clues of what they really are. And I see we have comments.
Yep. Scott. Okay, Scott. Hi, Scott.
It was.
Yep. And Janie too. Okay, thanks, Janie.
Very good.
So, okay, yeah, I'll start putting it together because I saw a few things, some of which won't really affect the everyday person, but they introduce some terms and give a reason why you should be concerned about certain things, even though the thing that I'll talk about doesn't affect you, but it'll be something that, might concern you with, because of it's similar to other things.
Alrighty then. So look forward to that. Is there anything left to work on for this citizen science project called Burst Chasers, Jeff? We've watched it and it went from needing help, this is a needs help project, to 44% to 54%. I was like, uh-oh.
Yeah.
Are we going to have a project on Friday to talk about?
Yeah. Thursday or Friday early evening, we looked at it and it was in the needing help. So we figured, this will be one that we could do. And it was about 40%. And then Saturday, just the next day, it wasn't in the needs help. And it was,
which is good.
It started climbing up into the 50s. And we were wondering, how fast is this going to go?
Yeah.
But there's still some headroom in it.
And Dawn says, hello. Hey, Dawn. Thanks for joining us. Yes to cybersecurity. So there you go. Excellent. We really appreciate your input on that. And so stay tuned for that. Jeff, you want me to share the screen?
Sure.
All righty. Go ahead.
Okay. Another Zooniverse. All of this stuff, we've talked about these before. We'll get into about because that's different for each one, but
yeah,
all of these are all the same stuff. Unveiling the mysteries of the origins of gamma ray bursts.
Very cool.
Oh, that was one of our phones thing.
Yeah.
Okay.
Got 4 parts to this one.
Yeah. 2 of these are practice. So you're not actually classifying stuff, but it's good practice for.
And I think they give you feedback, right? I didn't try those. Yeah.
They do. I did.
Good.
And this is kind of what it looks like. Now, one of the things. Oh, and if you notice, it was up to 54%. Now it's back down to 42%.
They must have added some data to classify.
Mm-hmm.
But it does have 2 parts to it. Because I was playing around with it Tuesday.
Yeah, pulse shape.
And I was like, wait, I don't see the boxes parts. Like, oh, there's, you do the one and then the other. So there's kind of 2 different pieces to it. And I was thinking, well, don't dally because this is going to be finished fast if you would like to do it. But maybe they'll Maybe they'll keep adding material. I don't know.
Yeah. So NASA partner
Very
gamma
cool.
ray, yeah, gamma ray bursts can um, come from supernova, black holes, and neutron stars. And apparently, the shape of the pulse tells them where it, gives them a clue about where it came from.
Oh, no kidding. I didn't get that. But you read the about. I didn't
Right,
get that far.
So, and speaking of,
Yeah.
here we
good.
go to the about.
Always good stuff in there and the team
Yep.
and everything. So,
Yeah. What is a gamma ray burst? It's a burst of gamma rays. I mean, okay. However, it's a burst so bright that it can outshine our galaxy. So this is a view
whoa.
looking past our galaxy, and that whiteout was the burst being so bright that it basically whited out the instrument.
Can you bigify it a little bit?
Sure.
Yeah, I think you can. Yeah. Oh, that's better. That looks better on the screen. Yeah.
Okay.
Good. Thanks.
So yeah. So, and one of the things you'll notice is that it gets bright much faster than it got dim, because there was a, it had a big dim, it has a more of a slope off, but we'll see that later.
Yeah, they named that in the field
Right.
guide. I forget what they called it.
Yeah.
But yeah,
And
we'll
so-
go into the field guide a lot. There's a lot of good information there.
And so this should look familiar since we just talked about spectrums last time. This is a pretty interesting graphic, though, for two reasons. One, they give relative sizes of the waves. And it's not the amplitude. That's how strong the wave is. It's the trough to trough, or peak to peak. That's what we're measuring.
Ah, right.
And
okay.
I don't like the fact, although I think these would get hard to see if they kept them the same size. I don't like the fact that they have them going smaller, because that's not the way it works.
It's this way,
peak
right?
to peak,
Not the.
So they're not. It's not the size of the peak. It's the peak to peak. So peak to peak, a gamma ray is about the size of an atomic nuclei, which is why we can't use light to look at these very small things, because you can't see things that are smaller than the wavelength. I mean, visible light, protozoa. Ultraviolet can see molecules. You can't really see individual molecules.
No.
You need an electron microscope and other things to look at these things. So that's why now, if we had a gamma ray scope, we could probably look at atoms directly. But we use X-rays to look at molecules and crystals. So,
we use X-rays to look at a lot of things.
Yeah. And infrared wavelengths are about the size of a needle point.
Okay.
And low microwave, high infrared is about the size of a butterfly.
That's a pretty big jump.
Yeah. Would guess that a butterfly cannot see infrared, because there's no way its eye could trap that. Because it's just too big. Humans are about the size somewhere between radio and microwave. And microwaves are about the size of buildings. And they're given...
No, that says radio.
Radio, yes. And if you know anything about radio waves, and Daniel can, if he's listening, can tell us this, radio frequencies are sometimes given in meters. It's a 3 meter, because that's the size of the wave. And that's also the size of the antenna that you need to pick it up.
Hey, Cliff's here. Hey, Cliff.
Hi, Cliff. You got us in the beginning.
Yeah. He says internet's crap. But you're using Starlink? Okay, very cool.
Huh.
All right. I didn't know he got that, I guess. Okay, good.
Yeah.
Glad
now,
you're here.
One of the things is that if it's cloudy enough and rainy enough, microwave doesn't work. And so,
Is that what Starlink's based on? Microwave?
yes,
Okay.
actually had a customer who used microwaves beamed from a mountain through the valley that they were in.
Wow.
And the various farmers used a microwave link.
Okay.
The trouble is, when it rained, the water drops soaked up all of the microwaves.
No, okay.
Now, so they thought, hey, let's go with satellite. Well, satellite uses microwaves. You know, same water drops, just interfering with the transmission in the other from a different direction. That's all.
Yep.
So
Okay.
yeah, that didn't work out so well.
I didn't know they used microwave. Okay.
Yeah, and so it was just they just had really bad reception during the rain. So, and it was only because of this specific frequency. Another one is pine needles are really bad for cell phone reception.
Right.
Most pine forests can be dead zones because the length of the pine needles on average soak up the signal. Yeah. Learned that from someone who worked for AT&T. So
okay,
then
what else you got here?
Okay, yeah. Now we get into this. Looks very familiar.
Yep.
Just not high enough resolution to see the the absorption lines. But then this other scale, this is temperature. So the temperature to give us a specific glow, so 173 Celsius gives us a red glow. The brighter we get, or the hotter we get, the more it goes up there. Up until high violet, starting to get into violet, you're 9,700 Kelvin up here. And then to get into like X-rays, you're talking 10,000. Well, they say 10,000 Kelvin or 10,000 Celsius because
looks like million to me.
Or 10 million, yeah. Because by the time you're at 10 million, 274 degrees really doesn't mean much. So they're effectively the same. And but they did, since they're scientists, they did put the tilde there.
Okay. And Cliff says, yeah, the little white dots are Starlink satellites that ruin your images.
Yeah.
Well, yeah. It's a quandary.
Yeah.
Better internet coverage for people like Cliff. But yeah. Anyway, what else you got?
Okay. So gamma ray bursts emit light called photons in all wavelengths. But the first emissions are usually seen as gamma rays, which will be the focus of the project. Because they used to use gamma rays, and they probably still do, but I heard about it a while ago, is that when they got a gamma ray burst, they'd all swing their telescopes over to look at to see what caused it. And because the gamma ray bursts lead the visible light. Now, at one point they were thinking that this meant that that the shorter wavelengths travel faster than the longer wavelengths speed of light.
How would they know to do that if they couldn't?
Well, because you'd have one camera that sees a gamma ray burst and another telescope somewhere happened to be pointed at the same thing, and they just noticed that shortly following it. So
got it.
So then it became a thing to, gamma ray burst, take a look. But it's not true that, but then they disproved the fact that different frequencies travel at different speeds. Turned out that in the process, just gamma rays are emitted first because they're hotter. And if you've got an explosion going on or some other big event, usually the hottest part is the beginning. So the gamma rays are first. So that's part of why the gamma rays hit first. And by looking at the gamma ray part of it, you're seeing the very beginning of the explosion. Looking at the visible light, even if you find it, you're not seeing the very beginning. In fact, who knows, the very beginning might be far off, into, they're still considered gamma rays no matter how close together they get.
Got it.
But it's, they could be far off in this direction.
Okay.
And we might not be able to see them at the very beginning, or we could. I don't know.
Mm-hmm.
But so gamma ray bursts come in. So this is a graph of kind of what it looks like. And I don't know why they have them spread out like this. This is the afterglow, and they have the gamma rays, high emitting, high energy gamma rays, or very high X-rays, visible light, radio. But from two main physical mechanisms, the more common mechanism is through the collapse of massive stars.
Okay.
It produces a lot of heat, which basically means that the light is given off. Some of the light is given off as gamma rays.
Okay.
They due to gravity explode as supernova. And they also release intense gamma ray jets, which allows us to see them even if they're not pointed at us, because they can light up the surrounding gas. Because we wouldn't see these otherwise. If there wasn't any gas, they'd be invisible to us because they're pointed away from us. But they just happen to light up the gas as they go through them.
Got it. Which is visible. Which is
right.
The visible range. Okay.
Right. Yeah. Well, and then the lit up gas produces photons heading toward us. That's the main thing.
Okay.
It's kind of like shining a laser into a mist.
Mm-hmm.
The laser beam you can't necessarily see if it's a really dry day.
Right.
But if you're going into mist, it'll light up the mist, and you see that.
Right.
The other method of getting gamma ray bursts that they know of is two neutron stars whacking into each other, or a neutron star into a black hole. Because those have enough energy to produce a gamma ray burst also. So why are they so interested in them? Because it takes light a long time to travel from the distant universe to reach us. That's when we see things from the distant universe, we're looking back in time.
Yep.
In fact, gamma ray bursts are one of the very few events that can be detected directly out to the era when the first stars were expected to form.
Wow.
Because they're so intense. They're so bright that, even a beam that's headed right toward you has some spread.
Yes. And
over time, that spreads out enough that you can't really see it. But they're so bright that even though it's so spread out, you can see it.
Mm-hmm.
And in fact, it's so spread out, it's so bright that it can outshine our entire galaxy.
Yeah, we saw that in the one animation at the beginning there.
Yeah.
Yeah.
And so one of the main sources of these is the Niels Gorel Swift Observatory. Then they just call it the Swift.
That's not really one I've heard of before.
Yeah, I know. Me either. And before this.
Interesting.
So
who launched that? Well, it said NASA at the bottom there.
Yeah, credit is the NASA Goddard Flight Center. I don't know if it's probably ours, but I don't know because
ours being United States.
Yeah. Hang on, let's see if we can see this. Well, okay, it probably is NASA because there's an awful lot on it there. As
opposed to European Space Agency or Japanese or.
And they would give credit if it was launched by someone else. So
yeah.
It's
okay. I was just curious.
Well, me too. That's why I detoured.
Yeah.
Okay. SWIFT is a multi-wavelength space telescope.
So not just.
Yeah, meaning it can observe GRBs simultaneously across the light spectrum from optical to UV to gamma ray wavelengths.
Okay.
SWIFT was launched in 2004.
Wow.
Yeah. And it's been monitoring and detecting GRBs for 19 years.
Oh my goodness. Yeah, curious if anybody out there has heard about this because I just had no idea.
Okay. The video shows a summary of the Swift's GRB discovery when it observes 500 GRBs.
That looks like a really lot of good videos in this description.
There are, but most of them
Cool.
are things that we've seen before and other things, but this one we haven't. So I'm going to run this.
Oh, it's only a minute.
Yeah. Oh, I've seen this video before, but.
Oh, those are gamma ray bursts.
Yes.
Is it demonstrating that the spacecraft will slew over to the position of these?
Well, it's constantly slewing because in order to cover this amount of space.
Huh. That is a lot of gamma ray bursts.
Mm-hmm. In 19 years.
Oh, they're counting them.
Yeah.
The corner there, 290.
Yep.
Wow.
Yeah. Oh, and yeah.
And I know you have your volume off, so.
Yeah.
Yeah, if you want to go see this, folks, go and take a look at this website.
Yeah.
And this is on Zooniverse. It's Burst Chaser.
Yep.
That's the project.
And okay.
Oh, interesting. It slowed way down.
Nope.
I just thought that was the 19 years. Okay.
Yeah.
Got it.
No, wow. It wasn't. I think they ended at 2009.
Oh, okay. Got it.
So that's just the first 500.
Okay. Yowza.
Yeah. So they happen a lot, and
yeah,
it takes a big view of the sky. So it doesn't have to point directly at the star to see it. It can see it, you know.
Okay. So a wide chunk of.
Yeah, it has a pretty wide field.
Okay. Good.
So,
yeah, what's the why we need your help? I think the first go was with computers, right? Right.
The computers basically identified potential gamma ray bursts.
Ah, okay.
And they want us to, well, here, I'll read that. We need your help to flag and identify GRBs with specific pulse shapes. Not just the fact that they're there, because they know that already.
Oh, right. I remember, yeah.
See the field guides for more information on these pulse shapes.
Right.
And I'll talk about that a little bit more later. That will help astronomers solve the mystery of their physical origins. Your eyes can accurately classify pulse shapes and other patterns in the data that we haven't yet been able to teach a computer to spot.
Yep. Pattern recognition.
My contention is because they're not good at training on this, because the training for this is really abysmal.
Oh.
So do the practice ones.
The field guide has a lot of good stuff in it.
But still, even reading the tutorial and the field guide, a lot of your training takes place in the practice, because there's stuff that they don't mention. Okay. Yeah. So.
Yeah, I looked through the practice ones, but I didn't actually do the practice ones. And I think once you do them, they'll tell you, yeah, you got it right, or
hit or miss is what they say.
Oh, I see. Hit or miss. Okay.
And sometimes you hit and you missed because it was a multiple selection.
Oh, I see. Okay.
And they don't tell you this ahead of time.
Okay.
Necessarily. So it's kind of like, you have to learn while you're doing the practice.
Okay. I didn't actually do the practice. I wonder. Okay.
So your classification of these GRBs will help astronomers pinpoint the origins of these bursts and advance our knowledge of these mysterious and energetic events in the universe.
Yeah, and this one takes more than 10 to 20 people. I think it's, weren't they saying there was 100. One that was 100?
No, yeah.
That's like the limit or something?
Well, they have a retirement. Zooniverse works on a retirement thing. Once it gets to X number of classifications for a specific image, it will retire it. And so either say yay, nay, or whatever. And
this one has some rules. There's a couple different rules that they have to
bending and getting around
to retire it.
Yeah, they're bending and getting around some Zooniverse conventions just to get the data they want. So they're doing 100 classifications.
Yeah, I thought it was more than 10 to 100.
Well, 10 is the usual limit for retiring something.
Okay.
They want 100 to classify it if 90% of the people agree.
Right.
Otherwise, it doesn't get retired.
Yeah.
So they're really Um, you know, they're really trying to narrow this down and have us pick out shapes so that they don't have to.
The pattern recognition.
Yeah.
Yes.
Yeah.
Which we're good at. We're good at as people. So,
some people are good at.
Yeah.
Some people have very low pattern recognition.
You ready for the next to share again?
Yeah.
Okay.
So this is the team. Dr. Amy Leon, University of Tampa.
These are NASA people, it sounded like.
And professors and and students. Catherine Krylov, University of Tampa. Also a veterinarian. Okay.
Okay.
Hugo.
Oh, here's someone from outside the country.
Yeah. Cordoba.
Argentina, yeah.
Yeah. Danny Rellens, Utah. Holden from Texas. Bing Zhang from University of Nevada, Las Vegas.
Pretty big team.
Yeah, and from all North Bengal University in Delhi, India. So, all around the U.S. and a bunch of places around the world too.
That's cool.
Yeah, Rome.
And I think I read it, if I understood it correctly, that if there wasn't a 90-some% consensus, they would look at
that if it gets to 100 and they haven't gotten a 90%, they will look at it themselves.
Yeah, right.
Which.
So okay. there's really a lot that people can do to help with this one.
Yeah, this is where they and this is why it came off of the needs help. Yeah. They passed 100,000 classifications in less than 2 weeks.
Yeah, that went fast.
Yep.
It was good.
So they stuck that in the results just so that they could show it there, because they don't have any results yet because they're not done with classifications.
But they do make an acknowledgement,
right? Yeah.
For the contribution. Okay.
Yeah.
That's
because
cool.
This is, I think, the thing that's easy for them to edit.
Oh, okay.
The FAQ. This is actually very useful in a lot of ways.
Okay.
So you should read this. How do I switch from each workflow? Basically they recommend doing the practicing first.
Right.
And I'll do some of that too.
Which I looked at, but I didn't actually do the practice ones.
Yeah. How do I switch from each workflow? Is you hit the burst chasers here and go to the main page.
Got it. Because that's where those 4 links were.
Right. Yeah.
The 4 buttons.
There isn't advance or go back, in each workflow.
Yeah.
Can I see some examples of each pulse structure? They're in the field guide here.
Field guide, yeah.
And you need the field guide because the tutorials
it's a little skimpy.
Weak. Well, the first tutorial has 3 things: the welcome to, a little bit of info, and the thanks for doing this.
That's the first practice one, right?
And the little bit of info could have simply have been read the field guide because they didn't put any of it in the tutorial.
Yeah.
So this is something where you'll have to do a lot of reading before you start because they're not good.
Yeah, so, I looked over the whole field guide before I did anything, and I thought I managed to do the actual data set. Okay.
Right. Yeah.
I didn't feel like I missed doing the practice ones from.
Yeah.
But yeah.
Until you see the practice ones, then you'll see how you screwed up.
Oh, I see. Okay. Because but I didn't do a lot. I did 2 or 3.
Yeah. And since they need, a whole bunch to get a consensus.
Yeah, I won't mess up their statistics too much, I don't think.
Yeah. Basically, you'll always see a vertical blue region, or almost always, because apparently sometimes you don't.
Oh.
But if it doesn't have a blue region, despite an obvious pulse on the plot, because the pulse is too short, so the computer program failed to plot the blue region.
Oh yeah, that's what the computer picked up.
Right. So it picked up the fact that there was a pulse,
but not what kind of
or
pulse.
where it was.
Oh, okay.
The blue region, was, here's where it is.
Mm-hmm. Like in general, from somewhere in this range. Yeah.
Yeah.
Okay, got it.
Okay. When will we be done? Never. Sorry, the more I did this, the more frustrated I got with it.
Oh, interesting. I thought it was fine. But I didn't read all this stuff either. So
Yes, that's why I'm saying you probably were. Now, you might have been doing it correctly,
okay.
but from my experience doing the practices,
okay.
probably not.
Probably not. Okay.
Because there's stuff that you learn in the practice.
Well, that's good. You know, it's good to have a practice.
Well, yeah, but it'd be better to learn it before you practice.
Yeah,
But hey,
you know.
okay. Can you do it using the Zooniverse app on the cell phone?
Ooh,
no. You have to use the web browser on your cell phone to do it, because apparently some of the tools that they use aren't available in the phone app.
Okay.
What's the difference between a pulse and noise? They don't really
field guide.
Yeah, they say go to the field guide, but
yeah, there's stuff in there.
In short, noise will extend below the average line, below the zero line. So you'll get up and down. That's the easiest way to detect noise.
Yeah, well, we'll see the examples in the field guide.
When should I use the talk button? When you see any problems in the light curves, which is most of them. Sorry, we had different experiences.
Yeah, we did.
Some light curves have a period with 0 counts. What are those? When a light curve has 0 counts, it means the telescope cannot see the gamma ray bursts, and you can simply ignore those parts of the light curves.
Interesting. Okay.
Well, yeah. I mean, I don't know how that's. Yeah, it's if it doesn't show a burst, don't count it.
They're trying to be thorough.
Yeah.
Goof proof is good.
Yeah. If you want to learn more about a specific GRB, or can I learn more information? There's a eye on there, so that when you're
an information button, icon. It's an icon, really.
Which doesn't work on the practice ones, by the way.
Oh, okay.
Just saying. They keep saying, hey, you got this wrong. Click on the eye for more information.
Nope.
Yeah, no.
Not so much.
Yeah.
Okay. It works on the live ones, though, right? It's okay there. Yeah. Oh, good. Okay.
Okay. What is telescope slew time? Does it affect the light curves? The Swift Burst Alert Telescope are constantly looking all over the entire sky when awaiting a GRB to occur. When the telescope is slewed, I think is from one location to another, it is called the slew time. During this time, you may see the noise level change. And the light curve might change more or less noisy, or less noisy to more noisy, or vice versa.
So I think what this means is that it's going to move, but that introduces noise, right?
Right, yeah.
Yeah, and slewing is, moving whichever where it looks.
So, they want to know the shape of the pulse, how many pulses there are, symmetrical or asymmetrical. Mm-hmm. Does it peak, or does it peak and then slowly drop off? Mm-hmm. And also, are they part of one big pulse? So here's a little bit of boom, boom, and then a drop off.
So it's got 2 pulses in there, right?
Yeah.
Okay.
This was first and only GRB with confirmed origin of a neutron star merger.
Oh.
Because of the coincidental detection of gravitational wave.
Ah.
However, the burst also presents a soft tail followed by the initial pulse. So that's what that is.
Well, they say see figure below.
Yeah.
Yeah. Oh, the merger is the.
Yeah.
Interesting.
This is not what we're seeing. So this is.
No, we'll see just a piece of that.
Yeah.
Like the.
So this is the GRB start. So this is where it is right here.
Okay.
And this one's a fairly symmetrical one, but.
Yes.
But if you notice, this is a different range. This is 10 to 50 Kelvin. It looks fairly symmetrical. 50 to 300, not Kelvin. Kilo electron volts.
Okay.
It's sharp up.
Yeah.
and this down.
Right.
So this is pulse without high variability, pulse with high variability.
That would be the noise.
Yeah, that's the noise.
When there's a whole bunch of
Mm-hmm.
up and down within
Yep.
the whole
Yep.
range, that's the noise.
Gamma ray bursts crash course on astronomy number 40.
Oh, that looks useful.
Yep. Neutron star mergers.
I missed a bunch of videos.
Yes.
Darn.
Okay. That was the fact.
Oh, good stuff. Okay.
Yeah. Now let's look at the field guide. What is a pulse? Again, they already talked about this if you read the FAQ, which is not where this information really should be, but this is the pulse. This is the noise on top of the pulse.
Right.
And basically noise goes positive and negative around the average line. And that's, this is noise. This is up and down over the average line. I would have actually drawn this average line a little bit higher, but oh well. So some are fairly symmetrical. Some are messy. And some have
That's
a
pretty
die-off.
distinct.
Yeah. And this is right at the very beginning edge. So those are pulses. And those are the things that we'll be seeing. What's the blue region in the plot? It's where the computer says that it is. Now, however, the computer is not always correct, and occasionally a small pulse could lie outside of the blue region. So this is noise, but if there wasn't enough down to it and it was just this would be an example of a pulse. Too. But yeah, this is noise.
Right. And I noticed that it said that the computer, like in this one, go ahead, because it's got all this blue range, but you don't really see a pulse in there, but the computer somehow thought it was
if you notice, all of this noise is elevated over the zero line.
Ah, okay.
And so this is a pulse with a slow drop off.
Okay.
This is something that they don't actually tell you.
Interesting.
This is why doing the practice is good, because
okay. Yep, I definitely missed that.
Yeah.
There's a lot of field guide. It's good stuff though.
Major pulse structures. This is when you're doing the marking. And the practices don't actually show you how to do this part. You just have to do them.
And again, they're in two different places, two different. After the two practice ones, there's two different workplaces.
Could have, and we saw this before with one pulse, and then it's almost a symmetrical pulse, and then this one's a ramp up and down. And these are multiple small pulses, and you'll never see this in one of the practice ones. Here's a kind of messy symmetrical pulse.
Yeah.
This is this one might be a pulse, or it might be a pulse with a slow tail. But and this is definitely a pulse with a slow tail, because basically anytime it spends most of its time over the zero line, it's kind of part of a pulse, either multiples or
here's what I was thinking, because
now if you've got this is a major structure that includes another one, do the small box first, because you can't draw a box inside a box, but you can draw a box outside a box. So
right.
And again on this one,
that one's fairly complicated. Interesting.
Yeah. You don't see this in the practice either, but and then this is just a pulse with a slow drop off.
Yeah.
Don't mark each little because this is noise. You can see it better here, but this is kind of noise. The drop off is kind of going
only if there's a significant peak within the pulse itself
that's higher than the noise itself.
Right.
So if there was a peak up to here after some of this stuff, then that would be another pulse.
But those aren't. Those little ones aren't.
Yeah, they're just part of the noise of it drop off. And
that's kind of annoying how you have to go back up to get to where you were.
Well, what it is it's how you scrolled here.
Yes.
So if I scroll back up, I'll get to the top.
It's still kind of annoying.
Yeah, I know.
Okay.
So Simple pulse, pretty symmetrical, looks like a triangle.
What's the name of this one? This segment, it's
Only one simple
only
pulse.
one simple pulse. Okay.
And this is a simple pulse with a drop off, with a decay structure. See, if I go back up to the top here, I'll be back at the top here.
Yep.
Pulse.
Oh, there it is. Extended emission.
Yeah.
That's the term I was
and you see,
remember.
This is the one that looks like it's a single pulse followed by noise, but since it's above, they don't actually say that here. They're just giving it as an example.
Interesting.
So, just look for this.
Yeah.
Too noisy.
Too noisy to tell. Yeah.
Because everything is noise. I mean, could be a pulse right there, but it's so close to the noise that it's hard to tell.
And I think they give you an option for that.
Yeah, they do. But they also give a deceptive one of
there's an other in there, I know.
It's an other, and there's a can't tell, but it's not because it's too noisy. What?
Hey, that's how they want
Yeah.
That's how they want you to do it.
Fast rise and slow decay pulses. I think again, as long as the noise is above the, mostly above the zero line. And this one's a little bit more obvious.
I wonder why they have the two different, one's kind of more smoother and one's kind of like chunky. Were they two different detectors? I thought it was all one detector.
Yeah, I don't know. I think it might be different data batches. Could be two different detectors, because they did say something about multiple vehicles.
Oh, okay.
Or, showing these
okay.
Symmetrical pulse structure. Yeah, we've already covered that. Rapidly varying pulses with large structures.
I like the last one. I'm like, what? I had no idea, but you knew, so that was cool.
So this is, a lot of noise, but it's all above the line. So I'd almost give it a box like this, because
kind of more wider.
Yeah, because this is all part of the drop off.
Yeah. What's the top of this one called? What's rapidly varying pulses within a large structure?
Yeah. And now this is, if you notice, it kind of like, I would say that this is probably one or two
but
peaks,
this isn't describing how to draw the boxes around.
Right. No, it's just describing what that is.
Okay.
And yeah,
of pulse.
I actually haven't seen anything that they want to be classified that way. And talk hashtag.
Confused the hell out of me.
Yeah.
Where does this go?
If you have a specific type of question, like a crown pulse, is this an example of a crown pulse? So if you go to talk and you use one of these hashtags, it will let them know exactly what your question is. And
they want to use the exact hashtag too.
So that they can search for it, because
they
don't want to actually read what you're writing.
Well, I mean, if you've got many data points, thousands or hundreds of thousands of data points, you need a sort tool. So there it is.
Incomplete data. So.
Yeah, I saw one. It was like, well, even that one, it's within the blue.
Yeah, it's okay, but now it's possible that this thing goes, that this is a symmetrical that's that goes outside of where the data drop off was.
I don't know. See, now when you got that smooth line and then poop, it kind of jumps. That's an incomplete data.
Yeah. Yeah, because it's just drawing a line from one set of data to another. You okay?
I think I'll be fine, but.
And then here's just a short bit that's really noisy anyway, but.
Yeah.
So that's it for the field guide. Burst chaser. So let's practice. Pulse or noise?
Oh, and they want you to look at the red part, the red circled part.
Is this a pulse or noise in the red
circle? It's not even
circle?
the blue box. That's weird.
Right. But is it pulse or noise? It's kind of hard to tell.
Most of it's above the.
Yeah, but there's a lot. But it's followed and preceded by below. So it looks like noise to me. So let's just say this is noise. Hit.
Hits. Oh,
So,
you got it.
Hit means you guessed right.
Okay.
So
That looks like a pulse.
is this a pulse or noise? Yeah, that's a pulse.
That's a pulse.
This part's easy.
Yay.
Relatively. Is this a pulse or noise?
Hmm.
I'm going to say yes, because it's a
fairly
fairly big structure.
Looks like a pulse to me.
Yeah, that's over. Hits. Okay.
Nice.
Is this a pulse or noise? Well, it's all over. So I'd say it's a pulse, but it's a very noisy pulse.
Yeah. Hits. Okay. So it's good for feedback and it gives you.
Yeah. Is this
Are you on the right track?
in there? I'm going to say it's a pulse. One of these days I'll get it wrong.
Miss.
Okay. It's a bit hard to tell in this case, although this is probably more likely to be a pulse because most of the counts are above the 0 line.
That's what you picked, though. You picked pulse.
Yeah.
Okay.
And it is in the blue region. However, the level of ups and downs in the red circle are similar to those on its right in the white region. So we cannot be 100% sure that this is a pulse.
Nice. Use your best judgment.
In cases like this, one match. No, they say that I matched even though they say that I missed. And also, here's something that I don't like about this practice is that they tell you what you got wrong, but when you hit OK, you can't see what you got wrong.
Ah.
And you can't move that box to a side.
Mm-hmm. So you have to remember.
Yeah. So let's get on to the next practice one. Practice pulse shapes. This is where it gets okay. Now,
so here's where they actually tell you which kinds. One, a pulse with an extended emission. Other,
right.
Too noisy to tell.
Right. So here it goes up fairly fast and it's drop off. So I'm going to say pulse with extended. So this is next. Missed. It says
missed.
It's a one simple pulse. Okay.
Is that what you picked?
No, I picked with a drop off because.
Oh, I see.
That.
Okay.
Okay.
All right.
So then, one or more pulses with a symmetrical structure. Well, they said it's not slow decay, so we're gonna go with that. Done.
Oh, they actually let you do it again?
Okay.
Oh, this one, but you got to do this one over and over again, right?
No.
Oh, no, it's different. Okay.
There's 2 phases. I don't see any of these because it's not entirely because it's okay. So they're saying that it's neither.
Okay.
The pulse is clearly a simple pulse, but it's a bit hard to tell whether it's a fast, slow. Except that in other cases, that's exactly what they say it is. So
you're right. I probably did it wrong. I don't even see a blue band in here.
Right. Yeah, it's kind of right there. I'm going to say one simple pulse. Next. Okay, that's correct.
You got it right.
Symmetrical. I'm just going to say yes. Hit.
You got it right again. Okay.
Okay.
Interesting. Yeah, I completely whiffed through this.
Yeah. So here is followed by an extended emission. It's kind of.
Yeah, I would say so.
Well, except that this kind of looks like noise here, but
it's still up.
I'm going to say one simple pulse,
and then
because this is noise.
So we're on the first phase of it. Okay.
Missed. Pulse followed by an extended emission.
Ah.
Now it says look at the info button for more help.
What info button? Oh, there. Oh, it worked.
Yes, but okay. This time it actually did work. Other time it didn't work.
Does it not work in the first one, or did they get enough complaints to fix it or something?
I don't know. There's an initial pulse that lasts around 30 seconds. After the emission is too weak for our eyes to see. Since the blue region does not end until around 100 seconds, it tells us that there are some extended emissions after the main pulse.
Holy mackerel.
So.
No wonder they want 100 people to review these.
And this is just a practice. So
wow.
I'm glad. So.
Okay.
Yeah,
I probably did it wrong.
So there. So that's exactly what they said it was.
Okay.
This.
Almost seems to have the long emission and then another pulse in the middle there.
That's I'm gonna say
Noise.
that's
Okay.
noise. Yeah. So
All
pulse
right.
by extended emission. Okay.
Hey,
Yes.
that's what they thought too.
One or more pulse shapes, high rise with slow decay rate. Yep.
Okay. Missed.
It's too noisy inside the blue region to see any structures, even though that's exactly what they wanted on the first part.
Hmm.
You see,
Okay.
this is why this is bugging me.
I didn't do all that.
There's a pulse on the left of the graph after the initial pulse ends around 10 seconds. The emission is too weak for our eyes to see. However, because the blue region does not end until around 70 seconds, indicating that the computer detects some weak emissions after the initial pulse, which is exactly what they said with pulse connected with underlying, pulse with fast rise, slow decay. So,
Well, this is the thing. You can give them feedback.
yeah, I know.
You can let them know that
And here it looks like
their instructions could use refining.
I'm going to say pulse with extended emissions because take a look at this curve there.
Yeah.
It's probably only one simple pulse, but I'm going to say.
So, was this the same set you saw before?
Different.
Was
you see?
Okay, so they have a pretty good practice
followed
set.
by extended emissions.
Yes.
Now,
that's what I would have chosen.
One or more pulses with fast rise, slow decay.
Yeah.
That's what that. Let's see if that's. Oh, good.
Yeah, you got it right.
It's the same as the last time. Okay. So enough of this. Let's go on to
an actual.
Yeah.
Some of the work. Okay, cool.
Pulse shapes. This is again. Ooh, look, there's. Welcome.
Ooh, they added one.
Welcome. Continue. Oh, look, this is the same image we've seen before. Please answer a series of questions. Please. Okay. This is their training. Please answer a series of questions. For some bursts, the pulse structure may be somewhat ambiguous. Do not have clear. In such cases, please use your judgment.
Because again, 100 people.
This is kind of like, yes.
If they're like this, they'll check it out.
Yes, I mean.
I'm sorry, honey.
Welcome.
Let's go.
Yeah, let's go. Yeah. Okay.
Oh boy, it's a messy one.
Yeah.
Kind of looks like.
I'm gonna say
other.
That might be another, but I'm gonna go this route.
Okay. One or more was symmetrical. It's kind of symmetrical.
Kind of symmetrical, yeah. You see, I don't see any of these, not entirely because it's too noisy. And I have seen that in the training. They do show that for situations where.
Yeah.
But this looks like a pulse.
Okay.
So I'm going to say that.
All right.
There's no feedback here, so.
No.
Okay.
But they're going to have.
Yeah. One simple pulse.
Up to 100 people look at these, so that's good.
This is actually easier than the training. Followed by an extended emission.
Yeah. That's what I would say.
Now, one or more pulses with fast rise, slow decay shape.
Yep.
Basically exactly what we showed before.
Yep.
Okay. Yeesh.
Noisy. Noisy. Too noisy, I'd say.
Except that these are all above, so there's something there.
Yeah, but they're...
I'm going to try an other.
I did that some. Those are the same choices, though, for this part, right?
Yeah.
So it's kind of two-phase thing.
I don't see any, not entirely because, well, it is too noisy. Kind of.
It's noisy.
Yeah. It's too noisy in the blue region yet. Oh, by the way, you can pick more than one.
Oh, interesting. You can't unpick it, though, it looks like.
Yeah.
Oh, there you go.
Click on something else.
Okay.
Okay.
That's easy.
Yeah, that's easy. Yeah.
Yeah.
Okay.
Maybe I did okay.
Yeah. That's a whole lot less frustrating than the training was.
Sorry.
Where are the pulses? Okay, here's where you
the
fun
little
with
boxes. Yes.
Oh, more
Again.
tutorial.
Kind of skimpy.
Oh, look, they actually show boxes in the tutorial. Yay. If you've done these before, you can draw the box.
Yep.
Once you're done, you can actually move the boxes to
Yes.
change the shapes. And there's that X thing here at the top so that you can get rid of a box.
Can you pick up the edges or the corners to change? I picked up the corners to.
I think you can pick up the edge. Just moves the edge. The corner moves the
Both.
two edges.
Yeah. Okay.
Pulses in the study is loosely defined as the structure that is more than 2 times larger than the noise fluctuation. You see, this is actually good. Would have been nice to know this in the practice too. The pulse is more than
Maybe
2 times.
That's why I did okay, because I read all these tutorial pieces and the field guide.
You're saying all these,
and I didn't do any of the practice. No, there were for the practice ones too.
You read
there?
those as well.
Yeah, I read all of them.
They were.
And the field guide,
yeah.
But I didn't do the practice parts.
However, there are no clear-cut definitions between pulse and noise. Please use your best judgment. However, this is good to know. More than 2 times larger than the noise. Okay, so that's good to know. Oh, there's actually a little bit more training. Blue region in each graph marks the main burst emission.
What do you think they added it recently? I don't know.
I don't know, but usually the last one is just.
Yeah, let's go.
Thanks, folks.
Lego,
let's go. Yeah.
The logo, something.
Yeah. Most of the pulses lie within the blue region. Occasionally, the computer may be wrong, and there might be pulses similar to the figure above. What figure above? There is no figure above. Sometimes you'll see pulses separated by background intervals, in which case, please try to only bracket the pulse region, not the included background.
You know what I noticed too? When I was reading through these, I got the distinct impression it was someone who wrote it who wasn't a native English speaker.
Okay.
But these look different. These look like they've improved a little bit in the English speaking range part. Yep.
Pulse and.
So these are pretty cool. I'm
going to start down there since this is where it's easier to. Oops, no, stop it. Okay, I'll start up here and then change it.
Yeah. Later. Yeah, that looks pretty good.
Except that I want to move this line a little bit. Oh.
That picks the whole thing up. Yeah, you got to use the corner, I think, too.
I'll use this one because it's too close to the other one.
Yeah, that's right. Yeah.
Done.
Cool.
Oh, okay.
Oh boy.
Okay. This is in the practice. You'll see that this is multiple peaks in a structure. So, because it never goes down, so this means that it's part of all the same pulse. It's kind of like flashes in the middle of an explosion.
Okay.
Or sparks.
So you're thinking box the whole thing, three pieces?
Yeah, but you have to do the small ones.
Yeah, that's what I thought. First. 3 pieces. Okay.
Yeah.
Oh, and then you're going to wrap around everybody?
Yeah.
Okay.
Like this. And then. This is multiple peaks, but it does peak and then die off over time.
Right. And again, there will be a whole bunch of people inputting this as well. So don't worry about too much. That's the whole point there.
Okay, so that's enough of that. There's the talk. There's the collections. This is where people... I don't kind of get it. This is just like people found these interesting. I guess people have a different artistic sense than I do.
That's fine.
Yeah.
Or they wanted to save them. They thought something about it, or they want to ask somebody a question maybe sometime. Or
so recents. My recent classifications. So this is just my recent classifications.
All right.
Well, these are from the practices.
I don't remember seeing that in other ones today.
No.
Okay. All right.
Okay.
So that's a pretty good coverage of this particular project. And if they're going to add more data points, yeah, you got time. Mm-hmm. I was thinking, boy, you want to do it this weekend if you want to participate, but maybe not. Maybe you got a little more time. Maybe we could do it like for a whole week.
Yep.
I don't know. Anyway, we're going to go ahead with the stellar events for this week, and that's May 24th through May 31st. On the 25th, the moon runs low. 27th is Memorial Day in the United States, and Pluto and the moon are in conjunction. May 28th, the Globe at Night project starts, and I missed the last one. Sorry about that. This one goes May 28th through June 6th. We're going to be looking for just 2 constellations, one in the north and one in the southern hemisphere. In the southern hemisphere is Cruz. And we've been actually observing that one for 3 months, according to... Oh, thanks, Cliff. Yeah. Very interesting project, huh? And in the northern hemisphere, you want to look for, well, I say buutes. I've heard other pronunciations, too, for that.
Booties.
Booties, yes.
It's the booties.
And so you go to the app, you observe, and they've got it on a computer as well as your phone.
Or Boutte. John Boutte.
Okay. You observe the constellation from your location and report to the site. Now, for us, it'd be, clouds, because it's been that way for a while. We call it the May gray, right? Mm-hmm. May 31st is the last quarter moon, and Venus and Uranus are in conjunction. May 31st is Saturn and the... also, I guess. No, that's 31st. Saturn and the moon are in conjunction. In fact, Saturn is 0.4 degrees north of the moon. Is there going to be a occultation for this
probably in the southern hemisphere near the equator.
Okay.
It's
all right.
Close enough because since it's north of the moon, we won't see an occultation.
That makes sense.
In fact, it may end up being more degrees north of the moon.
It's going to be cloudy.
Yeah.
Right,
well, yeah.
So, and Neptune and the moon are in conjunction. May 31st is also a Friday, so it's our Friday night show. We've registered for an event tomorrow, and we'll report on that next week. Stick around to find out where we're going. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. And what inspires you the most for this coming week?
Okay. If you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, May 31st. We're going to ISDC 2024, and that's the International Space Development Conference tomorrow, and it's their 42nd.
Yeah, I think it's the 42nd.
And I don't know why they are not making a big deal out of that, but
no, right?
I guess because they're in the space industry, they want to appear less fanish, more serious. But I wonder, I should walk around there wearing a towel just to annoy the ones who are really too full of themselves.
You probably will not be the only one. Let's both take towels. Okay. We got little hand towels. We can do that. I like it. I'm glad you thought of that.
So next week we'll bring back some pics and video and share what we learned.
Cool.
And then maybe the week after I'll work on the cybersecurity one and dig up some more stuff.
I actually did hear back from the AAVSO people. They do not have availability until November. So that guest will be delayed.
Yep.
Sad because we did some AAVSO references recently. So
yeah. And just talking about the ISDC, Pam actually ran their 14th one in 1995.
Yeah, I think Dawn was involved with that too, right?
I think. Okay, I said but
I'm pretty sure.
I wasn't there.
Sure Dawn was involved with that as well.
She's here. She can say yes or no.
Yes, she can. Although it's a little bit late there, I know. So she might be.
Yeah, she might be
for
done.
now.
Yeah. It's also the first one that had the website.
We were the very first ISDC to create a website.
And was one of the first 10,000 websites ever created.
Yeah, I found that out kind of recently.
And that would mean that Agamemnon was one of the first 10,000 websites ever created,
If it
too.
was in that time period, yes, it would be.
Yes.
Yeah. Once upon a time, there weren't that many websites, and now
Yep.
there's billions of them.
Yes. And we went from, blue print on a black background to the very modern black print on white background sometime in our 5-year run.
Oh, you talking about Agamemnon now?
Yeah.
I see. All right. Well, that's going to be it for tonight, folks. We hope you can join us next Friday. We will report back from ISDC. It actually goes for Thursday, Friday, Saturday, Sunday. And I remember past years they had Monday too, because it's Memorial Day weekend here. It's a long weekend. So, and I know the tourism group had a Wednesday thing.
I think it's only Friday through Sunday.
No, it's Thursday. It's
I
Thursday.
thought Thursday was like a meeting for them.
Maybe.
Not open to the public.
Well, maybe. I don't know.
But in any case, it doesn't matter because that's past time anyway.
Yeah. But it is an annual event and it moves around the world. Usually in the United States. I know they've been in Canada. I'm not sure they've been out other places on other continents.
They say that they have, and I looked at the wiki and they have been, just not very often. Usually it's continental U.S.
And it changed radically. Like when we were doing ours, it was mostly a local chapter who took it and ran with it. Now there's an organization and they do all of them. They just go to place to place to place. Oh, thank you, Janie. Hey, let's do a shout out. Janie was here and Cliff was here and Dawn and Scott. And we really appreciate your participation. Yep. We do this for you. So, yeah.
Yep.
We'll watch for your comments between now and next week as well. So have a great week, folks.
Yep. And your feedback is greatly appreciated. So yes, I will be doing the cybersecurity. Yep. Just one hint about what I'll be covering. One of the topics. Try not to have anything in your home that talks to the outside world, like Ring cameras.
No kidding.
Oh yeah.
Wow.
They're the easiest way for someone to hack your network, especially companies. If it doesn't need to be accessed from the outside, make sure that it can't be. So that's
interesting. Oh, we got another one. ISDC. Yep, ISDC 95.
Yep, she was there.
Yes, very cool. All right, folks. Have a great week. We'll see you next
See ya.
Friday. Good night.
Good night.